All right, since this is the last time that I'll see you before at least some of you start the exam, I just want to give a couple reminders about that, which is coming on Monday. The first is that as I said, I won't be able to do an exam review this time, but you can find a recorded version on YouTube that is going to be almost identical to what we do this year anyway, so that could be helpful to you. There's a Blackboard practice exam that should open up on Friday or Saturday, and I think you get one attempt, so I encourage you to do that in your sort of final preparations for the exams. It's going to be the exact same length, the exact same types of questions, not identical ones obviously, but it'll give you a good idea of what the exam is going to be like. That'll be in Blackboard starting Friday or Saturday. And then the other thing is make sure if you haven't signed up at CASA, you do that soon. There should still be some times left, but it's probably pretty limited. And just like they did for the PA test, CASA will open up new time slots every night for the next day. So if you wait till the last minute, you might still have a chance, but it's not recommended. And then make sure you go to the right CASA location. I don't want to write down which one that is, but I'm pretty sure it's CBB, the same location where you took the PA test. So double check that. Make sure you go to the correct CASA location, because there are two, and occasionally we'll have students going to the wrong ones. Okay, so let's get on with what we're going to do today. The title slide says VSEPR, which is Chapter 4, but before we get to that, we need to finish up the last couple things from Chapter 3, the last things you'll need to know for the exam. And so today we're going to talk about the nomenclature of covalent compounds. Last time we talked about ionic compounds, where you name the metal first and then the non-metal, or in some cases the polyatomic anion, and you have to know the names and charges of all those to be able to do that. Covalent nomenclature, there's two types of covalent compounds, and I think in general it's a little bit more straightforward. So the first thing we need for covalent compounds, though, which we didn't use for ionic compounds, are numerical prefixes. So the names of most covalent compounds are going to have these prefixes in them to tell us how many of each element we have. So in covalent compounds, we're talking about nonmetals combining. They can combine in different ratios in many cases. That's what we call the law of multiple proportions. And that is especially true for covalent compounds, so we need to have these number prefixes to tell us how many there are. So if you have one of a certain element or one of a certain atom in the formula, it's going to be mono. 2 is di. You've probably seen these in other contexts. Tri. 4 is tetra. So the first few are maybe a little bit strange, and then after that it becomes just, I don't know if these are Greek or Latin origins. I always get those two languages mixed up, but penta, hexa, hepta, octa, nona, and deca. So this is as high as we'll go, is 10. So this tells you how many of that element are in the chemical formula when you have that in the name. One thing to keep in mind as we do some of these, the prefix mono, we're going to be only talking about the names of compounds that have two elements and two elements only. You will only see mono used in the second element in the formula. And so if the first element in the formula only has one, it just won't have a prefix at all, but you'll see this on the second one. All right, and we'll see an example of that later on, when to use mono and when not to. All right, so that's the prefixes that we need to know. Those should be somewhat familiar from other things that you've done. And so the type of compounds we're going to start with are called binary covalent compounds. And as I said, these have two and only two different elements. So we're not going to do anything more complicated than that. So the name binary, as you probably know, refers to two different things, and that's the same for this binary covalent compound. It's a covalent compound that has two and only two different elements. All right, and then when we're doing the nomenclature for binary covalent compounds, there are a set of rules that we follow that tells us which element comes first in the name. In general, you don't have to worry about those because we're going to give you the formula and you just name the elements in the order they come in the formula. But if there's ever any doubt or you want to know where these rules come from, here's what they are. So the first element that you name, so there's two elements that are in the formula, and the first one that comes in the name is going to be the element with the lower group number. So that, remember, the group number refers to the column on the periodic table that it's in. So it's the one that's further to the left on the periodic table, lower group number. So if you had a compound with nitrogen and oxygen, nitrogen is to the left of oxygen on the periodic table, so the nitrogen would come first in the name. Like I said, you don't usually have to worry about this because we just give you the formula and you name that in that order. And then the second point is if they're in the same group, though, so if we have a compound that's formed from two different elements in the same group, so for example, a sulfur and oxygen compound where they're in the same column of the periodic table, the higher period comes first. That's going to be the one that's lower down in the periodic table. So a compound with sulfur and oxygen, you would put sulfur first and then oxygen. It's lower, it's down in a lower row of the periodic table or a higher period number. And the other thing to keep in mind is that for the second element in the formula, so for the first element, it may have a prefix if it's going to that tells you how many of that element there are, but then you don't change anything about the name of the element. But then for the second element in the name, whatever comes second, you're going to sometimes have a prefix, or I guess you always have a prefix for the second one. And then you're going to also have an IDE ending. So even though IDE in the context of ionic compounds refers to things forming negatively charged anions, covalent compounds use that as well. And we're not forming ions in this case. They're covalent compounds where they're sharing electrons, but you still put that IDE ending on the second element in the formula when you're naming it. So there's a couple of differences from the ionic formula that in nomenclature that we talked about last time. The first one, as I've already mentioned, is the use of prefixes. So that list of prefixes that I gave you on the first slide, they're used in combination with the element names to denote how many of each element there are. How many of each atom in the molecule, or how many of each element in the formula. However you want to think about that. And then the other difference between ionic and covalent compounds, when we're talking about the chemical formulas, the formulas that tell us the ratio of the elements that are in that compound, for ionic compounds we always said that you want to get to the smallest whole number ratio, so it would be NaCl, not Na2Cl2. But for covalent compounds you do not reduce it to the lowest ratio. All right, and the reason for this is that when you have a covalent compound, there are many examples of compounds that have the same ratios of elements, but they're actually different compounds where they have different absolute numbers. So for one would be NO2 is what we call nitrogen dioxide. That is going to be a distinct compound from N2O4. So these two would both have the same ratio of nitrogen to oxygen, 1 to 2, as the smallest whole number. But these are in fact different compounds. So you would not want to change the ratio from N2O4 to NO2, for example. You would leave it as whatever ratio, whatever set of numbers it is. Okay, so we don't change those to small whole number ratios for covalent compounds. We leave them as they are. All right, so as a few examples of these, we have, and again, I think once you learn the prefixes, I think covalent compounds are even easier to name than ionic. We have SF4. So this is one where we have 1 sulfur and 4 fluorines. So the prefix that means 1 is mono, but as I said, we don't put that on the first element. So if sulfur comes first in the formula and there's only one of it, we just say sulfur. We don't include, so there's no mono on the first atom, as we said, first element. And then the second part, we have 4 fluorines, so the prefix is going to be tetra. And then we change the ending from fluorine to fluoride, just like we would for ionic compounds. This is sulfur tetrafluoride. Okay? So you don't put the mono on the first one, and then the second one always going to have a prefix of some sort. P2O5, we just have to look at the numbers, and that's going to tell us the key parts of the name. So this is di, and this is penta. And then we would have, so the first part of this is going to be diphosphorus. We don't change the name of the first element, we just put the prefix on. And then for the prefixes that have vowels in them, which I think is, or that end in A, I suppose, if you're pairing that with another vowel, you usually leave it out. So that's a small detail that I don't think is going to come back to bite you at any exam or anything, but it would be pentoxide, not pentaoxide. So you don't put the two vowels next to each other for things like, I guess, tetra, penta, hepta, all the ones that end in A. You would drop that A out if it's partnered with something like oxygen that also starts with a vowel. Small detail there, but just something to keep in mind why I spelled it that way. And I think going from name to formula is even easier because, remember, if you know the prefixes, you don't have to worry about all the little spelling details or when to use mono or when not to. You just look at the name and translate that into numbers. So nitrogen trichloride, if there's no prefix on the first element, that means there's one of it. Tri means 3, chloride, so it's just going to be NCl3. All right. As a reminder for the exam, you do need to know the names and symbols for the first 36 elements. So if we gave you the name like this, you would have to know that nitrogen is N and that chlorine is Cl. Those are both within the first 36 elements. So remember, your periodic table doesn't have the names on it, so that's one drawback of the periodic table we give you. You do need to know the symbols that go with which elements for those first 36. And then disulfur decafluoride, disulfur is S2, deca means 10, so there's going to be 10 fluorines, S2F10. Okay? All right, any questions on that? All right, the last bit of nomenclature we have to do are what are called acids. So we're going to talk in more detail about acid-base chemistry in chapter 6, I think it is. But we're going to learn how to name them now because they are another type of covalent compound that we're going to need to learn how to do the nomenclature for. So what's the general definition of an acid? They're technically covalent compounds. They're anions and they're paired with hydrogen, which you can formally think of as H+. All right, so it's not really an ionic compound because it's all nonmetals, but it is, instead of having a metallic cation paired with the anion, you have a hydrogen in the form of H+ formally. Okay, so binary acids there's two types of acids we're going to name, binary acids and oxoacids. So binary acids, as the name implies, are also just two elements, and it's going to be H+ with a monoatomic anion. So those would be the anions derived from the nonmetals on the right side of the periodic table, like chloride, bromide, iodide, sulfide. So you would just have however many hydrogens you have is going to be equal to whatever the charge is on the anion to balance that charge. So if you have an acid with fluoride F-, that would be with one hydrogen to balance the -1 charge, HF. Right below that, of course, you'd have HCl, HBr are common ones. So there's not too many of these that we have to worry about. One that's a little bit strange is H2S. So sulfur is S2-, sulfide, and so it needs two hydrogens to pair with it to make the neutral compound H2S. I think that's the only common binary acid that has two hydrogens in it. So they're those ones that are just combinations of one element from the right side of the periodic table with hydrogen. The way we name these binary acids is it's a little bit of a convoluted name. So you have a prefix hydro that tells you that it's an acid. The second part of the word is the root name of the anion. So this root name applies to whatever anion the hydrogen is paired with. You have a suffix on the name, which is IC. So all of this is one word. Hydro plus root name plus IC. And then you have a second word, acid, to make it blatantly obvious that it's an acid, in case you weren't aware of that already. So that's kind of the formula for naming these. So as an example, HCl, you start with hydro, and there's no prefixes in these names. It's always just this formula here. No other prefixes besides hydro, no numerical prefixes, I should say. Hydro, chlorine is the anion, so you put the chlor in there. You change the N to IC, so it comes chloric, and then a second word, acid. So HCl would be hydrochloric acid. H2S would be hydrosulfic acid, I suppose, although it's maybe hydrosulfuric. It's more commonly referred to as just hydrogen sulfide, honestly, but that's a weird one. But it would be, I think, hydrosulfuric acid. You keep the sulfur in that case. But the key point is that for binary acids, you need to have the prefix hydro at the beginning. That's what denotes it as a binary acid, and of course the word acid tells you that as well. Now the other category of acids are called oxoacids. So they still have hydrogen at the beginning of the formula, formerly as H+. It's still paired with an ion, but in this case they're paired with polyatomic oxoanions. So if you've been studying your polyatomic anions that we introduced last time, you know that a lot of them have oxygen in them. So you have, the one we drew the Lewis structure of was NO3-, which is nitrate. That's a anion with a bunch of oxygens in it. You have the whole perchlorate, chlorate, chlorites, hypochlorite series with different numbers of chlorine and oxygen. You have sulfate, phosphate, all these ones that are, you're going to have to, you want to learn those for the test anyway. And those can also form acids when you pair them with H+. And again, the number of hydrogens that they have is determined by the charge of the anion. So if it's a -1 anion like NO3-, to make an acid from that, you would just put one hydrogen on there because that's a 1- anion, so you just need one H+ to balance the charge. If you had sulfate as your anion, which we know is SO4 2-, has a 2- charge, this gets 2 hydrogens to balance the charge. So those are the formulas of those oxoacids, where you take the anion and then add hydrogen to balance the charge. And the way that we name these ones is we don't have a prefix on them. It's just going to be the root name of the anion. And then there's a suffix that goes on, which is either IC or OUS. And we'll distinguish those here in a second. So that's the first word, root name, plus you change the ending. So from usually these have ATE endings as anions, nitrate, sulfate, chlorate, all those. You change that ending to either IC or OUS. And then, again, the second word is just acid. Now, when do we use which suffix? If you have an anion that ends in ATE, that becomes an IC ending for the acid. So nitrate would become nitric, and phosphate would become, well, that's a weird one, it's phosphoric. But it always would take the IC ending. And then if you have an ITE ending for your anion, so chlorite or nitrite, for example, that's when the one that becomes OUS. So it would be nitrous acid if it's NO2- nitrite. So there's two different endings depending on the name of the parent anion. So you do really need to know those polyatomic ions well to be able to name both ionic compounds and to be able to do the names of these oxoacids, as we call them. All right, let's do a few examples of acid nomenclature to wrap up this part of the course. All right, so we have, we want to know the molecular formula for hydrofluoric acid. Okay, so remember that the key part of the name that we look for is this prefix hydro. And that tells us that it's a binary acid, which means it has just hydrogen and something else. It doesn't have any other elements besides hydrogen and whatever the anion is. And so if it's fluoric, that means the anion is F, which we know is F-. It's on the second to last column of the periodic table. And so we pair that with H+ to balance the charge, which becomes HF. So because it's binary, we can eliminate choices B and C because it should only have two elements, H and F, if it's binary. And then finally, if you look at A and D, they're the same thing written in the wrong order, or different, sorry, in the opposite order, and the one that's correct is A. So by convention, when we're writing the formulas for acids, we put the hydrogen first. And in general, if you want to know, what is, if you want to be able to recognize an acid quickly, look at the chemical formula, and if it starts with hydrogen, chances are it's an acid. And so when you have hydrogen paired with other nonmetals and hydrogen comes first in the formula, that often means that it's an acid of some sort, and that we want to follow those rules for naming it. So this is hydrofluoric acid. And then finally, number 2, we have give the proper name for H2CrO4. So again, for this, we have to be able to know how to name these anions. So the anion that this is an oxoacid, so it's going to be the CrO4, and then the charge on that is 2-. We should know that, but we can also see that there's 2 hydrogens, which means the anion has to be 2-. And if that's the anion, the name for that you should know is chromate. But then if we want to change that to an acid name, the 8 becomes an IC, and then we add on the word acid. All right, so it's going to be C-chromic acid. We just change the ATE to an IC and add the word acid on. All right, so the rest of these don't make any sense because they have either prefixes, which we shouldn't have, or the wrong suffix in this case. All right, I think that takes us to the end of Chapter 3. So I'll put a little note here. This is the end of Exam 1 material. Ideally, I would have finished this a little bit earlier, but we're still getting messed up by the cancellation at the beginning. But we're now caught up with Exam 1 material. And so now we're going to move on to Chapter 4. So any last questions on this stuff before I move to a totally new topic? All right, so what Chapter 4 starts with, Chapter 4 is going to be all about the structure and bonding in molecules, primarily covalent compounds is what we're talking about in this section. So the first thing we're going to talk about is how to predict the three-dimensional shape of a molecule. So we worked through last time how to draw Lewis structures, which are the sort of two-dimensional orientation or representations of molecules where we just put we just arrange the elements in whatever way we decide to. Now we're going to learn how to take that Lewis structure and translate it into a three-dimensional shape and define that, and then talk about some of the key properties that arise from the three-dimensional shape of a molecule. All right? So the technique we're going to use to do this is called VSEPR. People often pronounce it VSEPR, even though the S comes before the E, which has always been mildly infuriating to me. But we'll call it VSEPR, or some people will say VSEPR, and that stands for valence shell electron pair repulsion. And the name VSEPR kind of tells you what this is all about, because we're taking around some central atom, we're arranging all of the valence electron pairs, and we know that when they form molecules that some of those electron pairs are going to be shared in bonds, some of those electron pairs are going to belong to that atom as non-bonding pairs or lone pairs, and we're going to take those, and we know that electrons repel each other, so we want to arrange those electrons as far apart from each other as possible to minimize those electron-electron repulsions. So really, VSEPR is not even much of a chemistry topic, if you ask me. It's more of a geometry concept where we're just going to place the electrons around the central atom. So we're always going to have some central atom as our reference point. We're going to place all of the valence electrons around that central atom in such a way that we minimize the electron-electron repulsions, or put them as far away from each other as possible. Because how much those electrons are repelling each other is determined by how close they are to each other. Place the electrons, I think I forgot a word, around the central atom, as far away from each other as possible. Okay, so things that repel each other, they want to be as far away as possible. If there's someone in this class that you don't like, you wouldn't sit next to them, you would sit on opposite sides of the room. It's the same thing for electrons. They want to be as far away from each other as possible, arranged around the central atom. That's what VSEPR does, and it's really just a geometric approach of saying, well, how many of these electron pairs do we have on the central atom, and what's the way that we arrange them such that they're as far apart from each other as they possibly can be. So there are two terms that come out of the VSEPR treatment, and we're going to want to know how to define both of these terms for the different molecules we look at. So one of them is called electron group arrangement. So this is a three-dimensional geometric shape. So if you have a good background in geometry, that will help, but it's not necessary because there's only going to be 5 of these shapes that we have to worry about, so it's not too many. It's a three-dimensional geometric shape, and this includes all of the valence electrons, so the bonding and the non-bonding electrons. When we're talking about electron group arrangement, we have to think about all of the valence electrons, including those that are not involved in bonds. Okay, so that's called electron group arrangement. And then the other part that comes out of this is what's called the molecular shape, or sometimes the molecular geometry. This is another three-dimensional shape. So there's some overlap between these. Some of them have shared names, but there's going to be some new shapes that arise. And for the molecular shape, we're only going to look at the atoms that are bonded to each other and sort of ignoring the lone pair electrons. So it's only the bonded atoms that we're thinking about when we define the molecular shape. So you can think of it as what the molecule looks like. Now why I say this is because the techniques that we have for visualizing molecules, so we want to know how do we prove what the shape of a molecule is. We use primarily X-ray techniques. This is a detail you don't need to worry about, but you can really only see the nuclei using that technique. The electrons are kind of invisible to you. So this defines the shape that the nuclei occupy that are all bonded to each other, ignoring any lone pair electrons that are also there. And the molecular shape also has some important consequences on some of the properties that are, and it's important to think about that in addition to the electron group arrangement. So basically, molecular shape, we ignore the lone pairs and define a shape that just the atoms themselves occupy. And that's the difference there, and we'll talk about both of those. All right, so some terminology to get us started before we go through all the different possibilities. I don't think your book does it this way, which is kind of a shame, but the way that I like to do it is using this AXE notation. So you have, A is basically just a placeholder, you don't even need that there, but then it's going to be X with some subscript M and then E with some subscript N. So A is your central atom, but we're only going to do geometries that have one clearly defined central atom, so it's not really going to be anything more than just A. X is an atom that's bonded to the central atom. And then E is a lone pair, again, one that's on the central atom. All right? So these subscripts M and N, which are going to be numbers, whole numbers, that's how many of each that you have. Okay? So, and the value of doing this is we can classify molecules into a very narrow and limited subset of electron group arrangements and geometry. You don't have to consider each molecule individually. So, for example, the molecule NH3 and PCl3, they might sound like they're totally different. They have all different elements, but they have the same AXE notations. They have the same basic shape. So by classifying molecules in this way, we don't have to. It's a nice classification system that allows us to quickly predict the shape. And the important part of this is the combination of X and E that we have. So how many atoms we have on our central atom, how many lone pairs. That combination together is going to dictate what the shape is, as we'll see. And these are referred to as electron groups. So when we say, what is the electron group arrangement, we're talking about the arrangement of both the atoms and the lone pairs around the central atom, includes the X's and the E's together. And so both those are referred to as electron groups. Now another term that I think is very useful to know, and that your book also I think doesn't use unfortunately, is what's called steric number. And this is the sum of N plus N, or the total number of electron groups. So it's how many total you have of X's and E's. And this I think is going to be an important one because, for two reasons. One, this steric number defines what the electron group arrangement is. So if you know the combination, the sum of M and N, how many total you have, it tells you right away what the electron group arrangement is, and there's only 5 possibilities we're going to deal with, so it's not that many to worry about. And then the other important part about steric number is things we'll talk about next time, or sometime next week, I guess, related to the bonding in these molecules and how that allows you to predict some things about the bonding in the central atom. So that steric number is an important thing for us to know. Now, an important note when we're defining steric number is that the bond order between A and X doesn't matter. It can have some subtle effects that we'll talk about at the end, but for defining the steric number or for defining the electron group arrangement that comes from this, we don't have to worry about bond order. Okay? This steric number is essentially the number of things that are attached to the central atom, and it doesn't matter if those are attached by a single bond or a double bond, or if they're just a lone pair. They all count as one item or one entity. Okay? And so no matter how it's bonded to the central atom, X will only count as one electron group. And another important subtlety that I should point out now is that this E in the formula is a pair of electrons. So it's for the non-bonding electrons, it's not how many total you have, it's how many pairs you have. And same with the bonding pairs, those are pairs of electrons. So really it's the number of bonding pairs that you have that's important in non-bonding pairs. And then an important parameter that we'll define once we know the molecular geometry is the bond angle. So let's define that now before we start seeing what those are. And it's the angle between two atoms that are bonded to the central atom, two bonded atoms, with the central atom as a vertex. Alright, so if we have water, H2O, the bond angle in H2O is this angle here. You start at one of the atoms that's bonded to the central atom, you go to the other one, and this is your center point of the angle. And so we abbreviate that as with an angle sign, and then it would be the three atoms that are involved, HOH. Alright, so that's the bond angle for that molecule. Some molecules will have more than one bond angle. If they have more than three atoms, they're going to have bond angles defined between every set of three atoms that includes the central atom. So there's going to be more than one bond angle sometimes, but it's defined as an angle between three atoms, basically. They're all contiguously bonded to each other. All right, those are the definitions. So now let's go through the different possibilities for electron group arrangements. All right, so if we have two electron groups, that's the smallest we're going to go to, where we have two things attached to the central atom. Let's go and look at what that looks like. So there's this simulator. I have the link here, and I'm going to try to use it in class today because I think it's really a nice tool. So if we have two electron groups, we want to put them as far away from each other as possible. They're going to be arranged 180 degrees apart, right? So the purple atom is the central atom. The two white ones are the outer X atoms, and they're, as you can see, 180 degrees apart. So that's the way that we arrange them to make them as far apart as possible. So the electron group arrangement is what we call linear. So any combination of two electron groups is called a linear electron group arrangement. And then there's two different AXE notations that would have a total of two electron groups. So one of them is AX2, that would be a central atom, two bonded atoms, and no lone pairs. And what we'll see as we go through this is that if you have no lone pairs on the central atom, if it's just AX whatever with no lone pairs, then the name of the molecular shape or geometry is the same as the electron group arrangement. So AX2 would also be called linear. It's a linear molecular shape and is an linear electron group arrangement. And the bond angle is going to be 180 degrees. Alright, so that's AX2. If we have AXE, that would be a situation where we have a central atom. There's a few things that would have this arrangement. And then you have one lone pair also. So it's still two electron groups, so it's still a linear electron group arrangement. This would also be a linear geometry. And this one's, I think, trivial. There's no bond angle defined because it's only two atoms. You need to have three atoms to define a bond angle. And what we should recognize is that all diatomic molecules, that means molecules that have two atoms only, will be linear. We don't have to think about them. That's, I think, a trivial outcome. Because we have two things attached to each other, they have to define a line, or a line segment, I guess is. So I give this one to be inclusive, but it's sort of a trivial and stupid one because it's only two atoms. Of course they're going to be linear. Okay? So that's what we have for two electron groups. Now let's see what happens when we add a third. Okay, so if we go to this simulator again and we add another electron group, We want to put them as far away from each other as possible. And so the way we do that is to put them into sort of a flat triangular arrangement. So you can see from this top view that it looks like a triangle with the 3 atoms. If we turn it over on its side, you can see that it's totally flat. So it's a planar arrangement of the 3 atoms into a triangular type of thing. So if we have 3 electron groups, that's going to be a trigonal planar electron group arrangement. And then within the trigonal planar electron group arrangement, there are 2 different AXE notations we can have, where again the total number of electron groups will be 3 for both of these. So if you have AX3, the electron groups arrange themselves in a trigonal planar fashion, and then all 3 of those positions are occupied by atoms that are bonded to the central atom, so it will look like this. And just like we saw before, if you have no lone pairs on the central atom, the molecular geometry is the same as the electron group arrangement. So this would also be called a trigonal planar geometry. And the bond angles, not as easy as 180, but still we have 3 bond angles that take us all the way around the circle. Those are the bond angles that we just went through. 360 degrees is a circle, there's 3 of them, so 360 divided by 3 is 120. Okay, so the bond angles for a trigonal planar are going to be 120 degrees. Alright, and then if we do AX2E, let's see what that looks like. So we're going to replace, for AX2E, we're still going to have 3 electron groups, so they're still going to arrange themselves in a trigonal planar fashion, but one of those is going to be occupied by a lone pair, and then the other 2 will be occupied by the X's. We can look at that at the simulator real quick. So we take off one of these, we put a lone pair, and so that's what it looks like. It's only 3 atoms, so of course it has to be planar. You can't have 3 things that are not planar with each other. That's physically impossible. So you can see it's still planar, and you still have, sometimes it lets me rotate it, sometimes it doesn't. There we go, wrong way, but you get the idea. Okay, so we have 3 things still. So the electron group arrangement is still trigonal planar, but if we want to define the molecular geometry, we only talk about the atoms themselves. If you have 3 atoms total, there's only 2 possibilities, linear and bent. We keep it simple for you. And so we call this a bent geometry. Okay? If they're not 180 degrees, we saw the first one was 180 degrees apart, that's linear. If it's something other than 180 degrees, we call that bent. Sometimes you'll see also V-shaped. I think that's another term that your book uses that I've never seen before, but it is sometimes used, V-shaped. But I think that's fairly obvious. It's just a bent arrangement of the 3 atoms. Now in terms of the bond angles are largely defined by the electron group arrangement. So we said that 3 things arranged in a triangle like this have 120 degree angles between them. One thing we'll talk about a little bit more at the end is that when you have lone pairs that are opposing those angles, the lone pairs have stronger repulsion than the bonding pairs. So that's going to sort of push down on these a little bit, on these AX bonds here. And so your bond angles are going to be something a little bit less than 120 degrees. Alright, they'll be still close to 120, but at least a few degrees smaller than 120 because of the stronger repulsion from the this lone pair here, which sort of squeezes things. So imagine that I'm the bent molecule, and then my head's the lone pair. It's going to push down on my arms, and it's going to cause the angles to go down like this. Okay? So whenever you have lone pairs, they compress the bond angles that are opposite to it. And so for this AX2E arrangement, they'd be close to 120, but not exactly. Now the exact value you can't very easily predict. It depends on what A is, it depends on what X is. There's going to be a variation depending on what the actual molecule is, but it's going to be something smaller than 120 degrees for sure. Alright, if we go to 4 electron groups, this is the first time we have to start thinking 3-dimensionally. So for 4 electron groups, let's look at what this looks like. Okay, so this is a 3-dimensional arrangement now. Now, there's a couple ways to think about this, but one thing you can see is you have 3 of the atoms in a plane, and then 90 degrees to that you have the other 3 atoms also in a plane. So it's sort of 2 interlocking planes like this is one way to think about it. It kind of also looks like a 3-legged stool with something on top, right? So you have the 3 legs down here, something on top. So visualizing these shapes I think is helpful to understanding them. But we call this one tetrahedral electron group arrangement. Now the reason it's called tetrahedral is that if we take those four things and we connect them with vertexes, you have four triangles that make up that shape. So tetra being four, hedral meaning the sides. So four sides like you have here. This is what it looks like if you take out the central atom and connect all the outer atoms. So it's called tetrahedral. This is probably the most difficult one to visualize. It's the least intuitive, I would say. The way that we draw this is we do two of the bonds are going to be at an angle like that. But as I said, the other two bonds are going to be in a different plane. So the way that we show that the bonds are coming out of the board and into the board is we draw a wedge to tell us that it's. Let's do that a little bit better. We do a wedge coming out towards us, and then we do a dashed wedge going in that direction. So the one that's a solid wedge means that it's coming out of the board towards you. The one that's a dashed wedge means it's going into the board away from you. So it's the best we can do to indicate three-dimensional structures on a two-dimensional surface. Okay? And then for AX4, all four of those positions are going to be occupied by the atoms X's, and because there's no lone pair, this geometry is also called tetrahedral. And then the bond angles in this, there's really no easy way to rationalize this unless you're a wizard at three-dimensional geometry. The bond angle is 109.5 degrees. All right, so learn that number because that's going to be what we see all the time for tetrahedral molecules is 109.5 degree bond angles. Okay? So that's the angle between any two x's with A at the center. So all 1, 2, 3, there's, 6 bond angles, I guess, if I count them right, and they're all the same. So all the bond angles are the same for this one. All right, and then if we go to AX3E, we have still 4 electron groups, so we're going to put them in a tetrahedral arrangement. But now we're going to replace one of the electron groups with a lone pair. So if you take one off and put a lone pair in, we see that the 4 things are still arranged tetrahedral, but then when we're defining the molecular shape, we ignore the lone pair. And again, this looks just like a 3-legged stool with nothing on top, so we call that trigonal pyramidal, or it looks like a pyramid with a triangular base. Okay? Alright, so we put the 3 x's. Now, in reality, all 4 of these positions are equivalent in a tetrahedral. They're all the same bond angle and everything. So we can put the lone pair wherever we want. It doesn't have to go on top. But if we put it on top, I think that makes it easier to see the geometry as we name it, which is called trigonal pyramidal. And again, the bond angles are going to be largely defined by the electron group arrangement, so they're going to be something close to 109.5, but a little bit less. All right? So they're going to be something smaller than 109.5. Now there's one more geometry that involves 4 electron groups. So we can also have AX2E2, still a total of 4 things bonded to the central atom, but now we have 2 atoms and 2 lone pairs. So still, combination of 4 things, but 2 and 2 this time. And so if we go back to our simulator over here, we remove one of the atoms, replace it with another lone pair. This is what this looks like. Now, as we said before, if you only have 3 total atoms in your structure, there's only 2 options, linear and bent. And I think this one's pretty clearly bent, right? So that's what we would also call this geometry as well. So the electron group arrangement is still tetrahedral, but when you have 2 lone pairs, if we draw it in sort of the standard orientation that I did, all 4 positions are equivalent, so where we put those 2 lone pairs doesn't matter. They're always going to be 109.5 degrees apart from each other, roughly speaking. So if we put them here and here, it looks like this. An easier way to see this is to sort of turn it over on its side, as I did in the simulator, where we draw the 3 atoms in the same plane, and then the lone pairs would be sort of in orbitals going out of and into the plane. Sometimes referred to as the Mickey Mouse structure. And so you have this is the picture you get for AX2E2. This is another example of a bent geometry, or sometimes called V-shaped. Alright, so there are 2 electron group arrangements that give us this bent geometry that we've already seen. We saw AX2E was bent, AX2E2 is also bent, The difference between those two is in the bond angles. Okay, so for AX2E, they're going to be close to 120 degrees because that comes from the trigonal planar arrangement. This one comes from tetrahedral electron group arrangement, so the bond angles are going to be close to 109.5. Again, a little bit smaller because of the lone pair repulsion, but similarly still pretty close to 109.5. But still, you definitely expect it to be smaller than an AX2E bent structure. Okay, so these are going to be less than 109.5, and also because this has two lone pairs instead of one, if you're comparing the bond angles for this one and the one we did before that, trigonal pyramidal, all else being equal, you would expect the bent geometry to have even smaller angles because now there's two lone pairs that are pushing down on those AX bonds. Okay, so a little bit of subtlety there that's probably not too important, but we should at least think about. So that's 4 electron groups. The next one we'll do is 5. This one has a little bit of weirdness to it, but I think it's not too difficult to understand for us. So if we want to put 5 electron groups, and we want to put them as far away from each other as possible, there's actually, with 5 electron groups, a couple of different possibilities that are fairly close to each other in terms of minimizing repulsions. But the one that ends up working best, I didn't mean to do that, 1, 2, 3, 4, 5. Alright, so what this looks like, we have to get this in the right orientation. And I have to be really careful with this because it sometimes tends to flip things. Okay, so what we have here is 3 of the atoms are arranged in a triangle, just like you would have in a trigonal planar arrangement. So if you can follow the red dot that I have up there, these 3 are in a triangle, and then you have flagpoles that are sticking up above and below the triangle. So you have these, what we call apical positions, that are coming out of the plane of the triangle into it. So if we turn this on its side without it totally going haywire, what you can see is that, again, these 3 are in a triangle. You have one coming out of the triangle, one going back in the other direction out of the triangle. So that's what we call the trigonal bipyramidal electron group arrangement. It's not going to let me do this. Here we go. All right, so this is the electron group arrangement is called trigonal bipyramidal. And within this, there are going to be 4 different unique AXE structures that we can get. So this is the one, probably one that's most complicated. It has 4 different possibilities, 4 combinations of 5 things that we can put around the central atom. So for AX5, that's the one that has all atoms and no lone pairs. The way we draw this is we have a triangular plane that's sort of going to be perpendicular to the board. So we have three of them in a triangle. And then we have the 2 coming out, and for AX5, all 5 of those positions are occupied by atoms that are bonded to the central atom. Another way that's convenient to draw this sometimes is to actually clearly show the triangle, where you put the A in the center, you put a triangle around that with 3 X's on it, and then you put another X out of the triangle in both directions. So that's sort of 2 different ways of drawing the trigonal bipyramidal electron group arrangement. And if we have AX5, where there's no lone pairs, the molecular geometry is also called trigonal bipyramidal. Now this one has 2 different bond angles, so let's see what those are. Alright, so if we look at, let's do this one in red. We still have this triangle of atoms, right? These 3 X's are in a triangle. So if you have this angle here between 2 of the X's that are in the plane of the triangle, as we already saw, when you have 3 atoms in a triangle, the bond angles are 120 degrees. So this bond angle between 2 atoms that are both in the triangle is going to be 120. So the one that I'm showing in red is 120 degrees. And then we have another bond angle that would be between, let's say, this top atom here, this apical atom, and the one that is also then in the triangle. So that's another unique bond angle there between those 2. This atom on top is perpendicular to the triangle, so not surprisingly the bond angle then would be 90 degrees. Alright, so this is the only electron group arrangement where you have 2 different bond angles. You have 120 degree angles within the triangular plane, and then you also have 90 degree angles between the ones on top and bottom with those that are in the plane. Okay? Alright, so then the next combination that we're going to have for 5 electron groups is going to be AX4E. So we're going to replace one of the atoms with a lone pair. And for this one, we have to think a little bit about where should that lone pair go. So there are 2 different positions in this molecule. You can either put it on the triangle, where it would be 120 degrees apart from 2 of them and 90 degrees apart from the other 2. Or you could put it up here at the top. The lone pair could go on the top where it's 90 degrees apart. It's not exactly, I wouldn't say it's obvious where it goes, but there is one that's a little bit better in terms of minimizing repulsions. Because remember, the lone pairs have the strongest electron-electron repulsion. So you want to put that as far away from everything as possible. That sort of gets the priority of where it goes. And so, to sort of leave you in suspense for a second, let's replace one of these atoms with a lone pair. So we'll take it off, put a lone pair in. And what we see is that, if I can get it in the right orientation, without it flipping on me, the lone pair goes into the triangle. Alright, so this spot used to be occupied by one of the atoms. These 3 things are in the triangle. These are the 2 that are perpendicular to the triangle. So when you're putting lone pairs into a trigonal bipyramidal electron group arrangement, however many lone pairs you have, 1, 2, or 3, they all go onto the triangular part of the molecule. None of them are going to go up at the apical positions. Okay? So the first lone pair and any other lone pair after that goes onto the triangle. So when we draw the trigonal bipyramidal electron group arrangement, one of these triangular positions gets occupied by the lone pair. Doesn't really matter which ones, they're all equivalent, and then the rest are going to be occupied by the X's. Okay, so that's what it looks like. Now this one is a little bit hard to see what we call this shape. So if we turn it over on its side, it becomes a little bit easier to understand the name for this. So I'm going to try to turn this over onto its side here. And then what you can see, if I can do this without totally flipping it, because it sort of rocks back and forth like a seesaw. That's why we call it seesaw. Alright, and the other thing you can do if you have, there are molecular model kits, if any of you have them, I encourage you to use them in this part of the course. I have a set in my office, and I learned in kindergarten how to share my toys, so you're welcome to come see those as well if it helps you. So sometimes seeing these things in 3 dimensions is helpful, and especially this one here that we call seesaw. So if we turn it over on its side, it becomes a little bit easier to see why we call it seesaw. This is the electron group arrangement that I think, or the geometry that I think most people get confused on. Even when I teach graduate students in the fall, we always review this stuff at the beginning, and most of them forget or mess up seesaw. It seems to be the one that's the hardest to comprehend. But it's called seesaw. It's an AX4E arrangement, and there's a few examples of molecules that will have that basic geometry. Okay, the other 2 possibilities with 5 electron groups, still trigonal bipyramidal electron group arrangement, but different combinations now. So if we go to AX3E2, as I already told you, all of the lone pairs go onto the triangular part of the molecule. So if we replace this with another lone pair, what we'll see is yet again, we have now 2 lone pairs on the triangle, those 2, and then the 2 apical positions are still occupied by atoms. Alright, so both lone pairs are going to go onto the triangle again. They want to be as far away from each other as possible, so putting them 120 degrees apart is better than putting them 90 degrees apart. Okay, so the 2 lone pairs go out here on the triangle, and then the rest of the positions are occupied by X. And this name I think is pretty intuitive. We call it T-shaped. It's actually on its side right now again, but pretty clearly a T-shape that you have there. So we call this T-shaped. Now let's think about the bond angles for this guy. So all of these are ideally 90 degrees apart, right? These are the 2 apical atoms, and it's the angle between the atoms and the ones on the triangle, which are about 90. Because of the lone pairs, they are going to be compressed a little bit, so they're going to be something a little bit smaller than 90 degrees, but pretty close to it. I think I forgot to do bond angles for the last one, didn't I? Yeah. Alright, this one shouldn't be too bad again. You have the lone pair here, so you're going to have some repulsion from this. This is going to make this one less than 90 degrees. So that's between the apical atom and one on the triangle. And then the one that goes between the atoms on the triangle is going to be a little bit smaller than 120. So you still have two different bond angles in the seesaw arrangement, but they're both going to be very close to what they are for the regular trigonal bipyramidal, 120 degrees on the triangle, 90 degrees from the one that's above it. But it's a little bit smaller because of the lone pair. All right. So that's going to be, T-shaped is only going to be 90 degrees because now we only have one atom left on the triangle. Something I didn't mention, but hopefully is obvious by now, is that we only define bond angles between atoms. You don't define bond angles involving lone pairs. That's not really, that's a nonsensical definition of a bond angle. So it has to involve an atom that's in a bond, not a lone pair. All right, so let's do the last 5-electron group geometry, which is AX2E3. There are a few molecules and ions that have this arrangement. And so this one, we're going to put all three of the lone pairs onto the triangle. So the third one also goes there. And as you can see, there's only 3 atoms left. We only have 2 possibilities when there's 3 atoms, linear and bent. And this one I think is pretty clearly linear, if I can get it just right. There we go. So the 3 atoms in this case are linear from each other because we have the 3 lone pairs that are in the plane of the triangle, preventing them from being bent. Okay, so this one's going to be, get back to my blue pen. This one's going to be, again, trigonal bipyramidal still, electron group arrangement because it's 5 electron groups. All 3 of the lone pairs go on the triangle, leaving the 2 x's above and below 180 degrees apart. So there's only one bond angle in this molecule because there's only 3 atoms total, and it's exactly 180 degrees. So you don't get any compression from the lone pairs because they're pushing up on the top bond is the same as they're pushing down on the bottom one. So there's no net distortion of that. All right, so if my 2 arms are being pushed at equally from the top and the bottom, they're going to still stay where they are. It's, I guess, sort of a physics thing if you want to think about it that way. So you have those 2 possibilities, linear, and this AX2E3 is going to also be a linear one when you have 3 lone pairs instead of 2. All right, the last one, the highest that we'll go to, is 6 electron groups, AX6. Okay, so if we do AX6, we got to remove our lone pairs now and put a total of 6 on there. I don't think the simulator lets you go higher than 6, so even if we could, we won't. All right, so AX6 looks like this. Now what you have here, there's actually some similarities between AX5 and AX6. AX5, as we said, was a triangle with 1 above and 1 below. AX6 is a square with 1 above and 1 below. So you have 4 atoms in a square, and then you have one coming out of the square in one direction and one coming out of the square in the other direction, perpendicular to that plane. So if we turn this on its side, you can clearly see that those 4 are arranged in a square plane, and then the 2 that are above and below that square plane as well. Okay, so that's AX6. So I think it's pretty easy to draw and visualize this one. The name for this is not as intuitive. It's called octahedral. And again, that's more of a geometric origin for that name. Octa means 8. It doesn't mean that there's 8 things bonded to the central atom. It means that if you were to connect all of the outer atoms with vertexes, you would have 8 triangular faces. Tetrahedral has 4. This would have 8. So we don't need to worry about the origin of that name too much. We need to know what it is. So the way that we draw this is, again, you have a square plane. So you have 4 of your atoms are in the same square plane. And then the other 2 are coming up and above and below the plane. You can draw this perhaps even simpler by drawing the actual square with 1 out and 1 below. And the reason we call this octahedral is because if we were to connect all of the adjacent x's, you would form, this is 1 triangular face, you would form 8 of those triangular faces defined by 3 adjacent outer atoms. That's why it's octahedral. But anyway, this is the shape. It's a square with 1 coming above and 1 coming below. If there's no lone pairs, the molecular geometry is also octahedral. And the difference between octahedral and trigonal bipyramidal, as we said before, there's some similarities. Trigonal bipyramidal is a triangle with 1 coming out in each direction. Octahedral is a square with 1 coming out in each direction. The difference, though, is that in octahedral, all of the positions are equivalent and all the bond angles are the same. So everything is mutually 90 degrees apart from each other. So there's only one bond angle in the octahedral, 90 degrees. Every other X atom is 90 degrees from the nearest one to it. Okay? So there's only one bond angle to worry about. It's exactly 90. And then there's two other subclasses, two other molecular geometries that derive from AX6 that also have a total of 6 electron groups. So in AX5E, we replaced one of the X's with the lone pairs. As I said, because all 6 of these positions are equivalent, we can put the lone pair wherever we want. It's going to be the same distance from all the rest of them. So unlike trigonal bipyramidal, it doesn't matter where we put the lone pair. And so when we do that, we get this sort of picture, and the easiest way to visualize it is to put the lone pair on the bottom. And this we call square pyramidal. So it's a pyramid with a square base instead of a triangular base. So again, there's the square base, and then the one coming out makes it pyramidal. So we put the lone pair wherever we want, but the convenient place to put it to visualize this is on the bottom. So you have your square, you have your octahedral electron group arrangement. Put the lone pair in one of those positions. The rest of those are atoms that are bonded to the central atom. And this is what's called square pyramidal. Shoot, I put too many X's. I got a little bit happy there. There we go. Lone pair there. Square pyramidal. And the bond angles for this guy, again, are going to be a little bit compressed because of the lone pair repulsion. They're going to be a little bit smaller than 90. Okay, so it's still pretty close to 90, a little bit smaller. So you can almost think about this as like slight folding of an umbrella. You have the 4 X atoms here and the one on top, and you're sort of just puckering those out of the plane just a little bit because of the repulsion from the lone pair, but still pretty close to 90 degrees. And like I said, there's no way to quantitatively predict what those bond angles are because it depends on what A is and depends on what X is, but they will be something smaller than 90, but just by a few degrees usually. All right, the last one that we have to do, which also is from 6 electron groups, is AX4E2. So in this case, we're replacing 2 of those positions with lone pairs. So if we draw the octahedral electron group arrangement, now as I said, the lone pairs repel each other the strongest. So those get sort of priority. We want those to be as far away from each other as possible. So the way to put them as far away from possible, I hope is clear, is put them exactly opposite each other, 180 degrees apart. So the first lone pair doesn't matter where it goes because all the positions are equivalent. But once we add a second one, we want that one to be as far away from the first one as possible. So we put them 180 degrees apart. The other spots are occupied by X. All right, so let's see what that looks like in 3 dimensions. So if we put a second lone pair on, you can see that the 2 lone pairs go 180 degrees apart, leaving the other 4 atoms in the original square plane. And now we just have a simple square arrangement of the atoms, which we call square planar. Okay? So another way to draw a square planar is just to turn it over on its side and just draw them as a square plane. You would have a lone pair that's coming out towards you and another lone pair that's going into the board away from you. That's a little bit hard to draw in this orientation. But if you just look at the atoms themselves that you need to define the geometry, it's just a square of 4 X's bonded to the central atom. So I think a fairly simple one. This is called square planar, as I said. And once again, because you have the lone pairs that are arranged exactly 180 degrees apart, they push equally on the planes from both directions. So you don't compress any of the bond angles. They're going to be exactly 90 degrees still. All right. Now I had a really grumpy professor in graduate school who always wondered, why do we call it square planar? Because when have you seen a square that's not a plane? I think that's to distinguish it from square pyramidal, to be honest. But so if you see anybody calling it square, I suppose they're technically not incorrect because a square has to be a plane. The square planar is the more common way to refer to this geometry. It's one that we will see for. There's a few molecules that have the square planar geometry, not too many. It's not the most common one. So that's AX4E2. Now the last thing I want to talk about for VSEPR is a little bit more about bond angles. So as we've seen, when you have lone pairs in the structure and they're not opposed in opposite directions from each other, they can compress the bond angles because they repel more strongly. So there's two different groups that cause bond angle compression. So as we already saw, lone pairs can do that. And then the other one that can do that are multiple bonds. So even though at a sort of basic level, when we're counting electron groups, when we're defining geometries, it doesn't matter too much whether it's a single, double, or triple bond. If you have a double or triple bond, remember those have more electrons involved. Those have 4 electrons for a double bond instead of 2, 6 electrons for a triple bond instead of 2. So because they have more electrons, they do have a little bit more electron-electron repulsion involved with those. It's not huge compared to a lone pair. It doesn't affect things as much, but it is still a small factor sometimes. So if we had this compound here, if we drew the Lewis structure for CH2O, it would look like this. You would have also lone pairs and oxygen if you care. But anyway, if we're defining the geometry for this carbon here, normally this is a trigonal planar structure nominally because we have 3 electron groups bonded to carbon, oxygen and 2 hydrogens. So the bond angle should be close to 120, but because we have a double bond here that has 4 electrons instead of 2, we're going to get a little bit of repulsion on those bonds there. And so this angle here would be a little bit smaller than 120 degrees. And these angles here between the hydrogen and oxygen would be a little bit bigger than 120 degrees. Okay, not by much, but that's what we would expect because the double bond has a little bit stronger push than the single bonds do. So it's going to, again, because of that push, it's going to just push those down a little bit and compress the angle between the 2 hydrogens. At the same time, it has to elongate the angle between the oxygen and the hydrogens. Okay? So that's the effect of double bonds. I don't think it's one that's going to come up a lot, but it is another thing that can have a small impact on bond angles. All right? Now, the important thing also, as we've talked about, is that the lone pair repulsion is the strongest. So if you have 2 lone pairs on your central atom, that repulsion is the one that's the strongest, and so that's why we always prioritize putting the lone pairs as far apart from each other as possible. Okay, so in the geometries where we have 2 lone pairs, if there are more than one if there's more than one way to arrange those lone pairs, we always do that in the way that minimizes repulsions. So that's why for AX2E3, you put the 2 lone pairs on the triangular part of the molecule to make them 120 degrees apart instead of 90 degrees apart. Or if there's AX4E2, as we saw, you put them on opposite sides to keep them as far away from each other as possible. So lone pair repulsion is the strongest one. That's why that's going to be the first one you think about when you're defining the geometry and deciding where to put things and how to rank bond angles and stuff like that. All right, the last thing that I have today is just an example. Let's determine the molecular shape of PCl3. So PCl3, if we're going to do VSEPR and determine the molecular shape or the electron group arrangement, we need to first have a good Lewis structure. So we learned Lewis structures a little bit ago. Was it just last time or two lectures ago? They're all running together now. But we learned Lewis structures recently, and you have to be able to do that to be able to do VSEPR. Okay, so without a good Lewis structure, you're hosed. And so now the one thing about this, though, the nice thing about VSEPR is because single, double, triple bonds don't matter so much, you don't have to necessarily have the exact correct Lewis structure, but you need to have the correct number of lone pairs on the central atom and the correct number of things bonded to it, obviously. So there's some details of the Lewis structure that aren't very important for VSEPR, but you at least have to have the basics correct. So let's review how to do Lewis structure, since it is important for the next exam also. So we have PCl3. We have to count the electrons first. We may have done this one already, but I'll just go through the details to refresh you. So phosphorus contributes 5 electrons. That's because it's in the 5th group of the periodic table. Let's review that quickly in case that's not obvious at this point. All right, so phosphorus is over here. It's in group 5A, so that tells us it has 5 valence electrons. It's S2P3 valence configuration. All right, so it has 5 valence electrons, and then chlorine is 2 over from that. So each chlorine is going to contribute 7, but there's 3 of them. So you have 3 chlorines, each contributing 7 valence electrons for a total of 21. And then when we add those up, we have 26 valence electrons. All right, so this is one of the examples we did, but we'll go through it again. PCl3 has 26 valence electrons. We start out with single bonds to all of the outer atoms. We complete their octets by adding 6 more to each one. And by completing 3 octets, we've used 24 electrons. We still have 2 left over, so those last 2 then go in the central atom. All right, so you want to become proficient at doing this, not necessarily as fast as I did, but practice a lot and get used to this, because Lewis structures are important for a lot of things we do. And then from determining the molecular shape, we can do it in a couple of different ways. Now, if we want to write the AXE notation, our central atom phosphorus has 3 chlorines bonded to it, 3 other atoms bonded to it, so it's going to be X3. It has 1 lone pair there, so it's going to be AX3E, just 1 E. So that's the AXE notation. The steric number is 4, so that defines it as a tetrahedral electron group arrangement. But what we're interested in here is the molecular shape. So for the molecular shape, we have to account for the lone pair as well. And so with this tetrahedral electron group arrangement, I do think it is helpful to be able to draw things out, because you don't necessarily want to memorize all of these. But for AX3E, we put the lone pair in one of those positions, the chlorines down there, all tetrahedral arrangement, but then the shape that's defined, as we said, is called trigonal pyramidal. All right, so it's a trigonal pyramidal electron group arrangement, molecular geometry when you put one of the lone pairs at that position. All right, so that's going to be the answer for this one, trigonal pyramidal. And then what should be helpful for some of you is a bonus quiz. I'll have a table in the next notes that summarizes a lot of VSEPR. But because the Lunar New Year is upon us, it's also Valentine's Day, I suppose, but some of you get depressed by Valentine's Day, so I won't mention that. But it is Lunar New Year, which I think is a happy occasion for many of us. So I'm going to give you a bonus quiz to start that off. So as a reminder, you need to have the bonus quiz form. Kindly tear the page in half. It makes it a little easier for me to collect and organize them. And if you forgot one, hopefully you have a kind benefactor sitting near you. But it does have to be on the proper form to get credit. Just like before, I guess I'll stop the video here because the YouTube audience does not need